Hello everyone, my name is Jaehan Bae and I'm a postdoc at Carnegie Institution. Today I'm going to tell you about spirals driven by buoyancy resonances in protoplanetary disks. So I just wanted to start by reminding you that protoplanetary disks are three-dimensional objects. This is an inferred temperature structure of the HD 163-96 disk based on ALMA CO observations. As you can see, the disk has a radial temperature gradient with a hotter inner disk and a colder outer disk, but it also has a vertical temperature gradient such that the surface layers are hotter than the midplane, and this is because of the stellite radiation. Now, if you look at the right panel here, this is what we theorists often, but not always, use in numerical simulations. Here we do have a radially decreasing temperature profile, but in the vertical direction, we simply assume that the temperature is identical at a given radius. So, although such a setup is not as realistic as we want, but this isothermal has some advantages. First of all, this is the simplest thermal structure you can consider. So if you'd like to compare your linear analysis with numerical simulations, for example, this is the first thing you can try. And from the simulation point of view, we can obtain the hydrostatic equilibrium solution for the disk density and rotational velocity analytically, so it is easy to implement the initial conditions into numerical simulations. And of course, because we don't solve the energy equation, most of the time this means that simulations run faster than otherwise. But what I'm going to tell you here is that by imposing such a simplistic thermal structure in numerical simulations, we can miss some interesting physics. And this is one example, buoyancy resonances. So if you look at this equation here, G is the gravity, gamma is the adiabatic index, and in the parenthesis, this is log of P gas pressure divided by rho gas density to the gamma in the power. So this is what is called as buoyancy frequency. And let's consider a gas blob here in the disk and let's perturb it vertically. Then when n squared is greater than 0, the gas blob will vertically oscillate around its equilibrium position. When n squared is 0, that means that there's no buoyancy. So the gas blob is displaced, but it won't move any further. When n squared is negative, the gas blob will further rise because it is unstable to the perturbation, and it will rise until it meets a layer where n squared is greater than 0 or equal to 0. So going back to this locally isothermal disk model, let's see what happens for n squared. If we plug P equals rho times Cs squared, where Cs is the sound speed, and if we use gamma of 1, so it's an isothermal equation of state, you will get n squared of 0. So what that means is that, again, there's no buoyancy in the disk, in this simplistic disk model. But when the disk has a positive vertical temperature gradient, and when gamma is equal to or greater than 1, if you substitute the ideal gas law, and if you think about this term at the bottom, temperature increases as a function of height, and density decreases as a function of height. So this term, the derivative of this term is always greater than 0. So n squared is always larger than 0 in vertically stratified disk. So in vertically stratified disk, this buoyancy motion is a natural oscillation. At each location in a disk, there will be these vertical oscillatory motions. Now, what happens when there is a planet in the disk? The planet orbits around the center star at a fixed orbital frequency. So there will be certain regions in the disk where the buoyancy frequency and the planet's orbital frequency match with each other. When that happens, the buoyancy oscillation can be amplified by the planet, and this is what is called buoyancy resonance. And I'd like to point out that there's this thermal requirement for buoyancy resonances to operate. That is, cooling timescale has to be longer than 1 over buoyancy frequency. Otherwise, gas will cool down efficiently and it will adjust itself to the circumstance, and there will be no buoyancy. So to test this theory with numerical simulations, we adopt a disk model of TW Hydra as one of the motivations, as I will show you later, of this study is to explain spirals observed in the TW Hydra disk. So we have a planet at 90 AU with a mass of half a Jupiter mass, and we adopt an adiabatic equation of state with gamma of 1.4, and the cooling is realized through thermal relaxation over relaxation timescale, prescribed relaxation timescale. So I will show you two models. The first one is rapid cooling model. So the gas cools through radiation and diffusion. So you can think of this as more isothermal calculation because of the rapid cooling, and this is similar to what most of hydrodynamic simulation assumes. The other model is a slow cooling model, and the idea behind this slow cooling model is that if you think about how gas would cool in protoplanetary disks, because most of the mass is in hydrogen molecules, which we know are poor emitters, those molecules have to first lose their energy through collisions with dust grains, and then grains radiate away the excess energy, right? But if you are near the surface, because dust grains are settled down to the midplane, you don't have many or sufficient grains to collide. And that's the idea behind this slow cooling model. So because of the infrequent gas dust collisional rate, the cooling of the gas can be limited. You can think of this as more adiabatic simulation because cooling is very slow. So to begin with, this is the result for rapid cooling model. From left to right, you see perturbed density, perturbed temperature, and vertical velocity. And the planet is again at 90 AU. That's a half a Jupiter mass planet and the azimuth of 0, so at the middle of each panel. And this is what you see. And this is pretty much what you have been seeing in typical planet disk interaction simulations. You have a planet, it excites a spiral in the inner disk and one in the outer disk. Those are driven by Lindeblad resonance. And there's a secondary Lindeblad spiral here, this one. Now, moving to slow cooling model, I will run this one. And you can see that there are the spirals driven by the Lindeblad resonance, this outer one here, and the inner one here, and the secondary here. But in addition to those Lindeblad resonance-driven spirals, you see a family of very tightly wound spirals, and those are what buoyancy resonances drive. So to compare these two models side by side, again, you see consistently the Lindeblad spirals, but you get additional spirals driven by buoyancy resonances. So what we have done next is that this is the model from the numerical simulation. Planet is at here, and you see that vertical velocity perturbation is about plus or minus 50 meters per second. And yeah, there are blue shifted and red shifted spirals. They are very tightly wound, as you can see, almost annular. And we ran it through radiative transfer calculation to obtain 12 CO emission. And this is the result. So simulated ALMA observation of 12 CO with 0.1 arc-second beam. And you can see a consistent feature, the spirals, red shifted one, blue shifted one here, pretty tightly wound, that is consistent with the numerical simulation. And the right panel here shows the data, actual CO data we published last year of the TW Hydra disk. And you can see that there's this arc here, red shifted one, and blue shifted one here, and additional red shifted one here. And they are very tightly wound. And if I plot the pitch angle, that is measuring how open or how tightly wound a spiral is, that the angle is shown with blue dots here for the data, TW Hydra data. And you can see that between about 70 AU to 150 AU, you get pitch angle less than 10 degrees. And traditional theory, the Lindelblad resonance, you can get only, you get very large pitch angle, especially near the planet. The pitch angle is as large as 90 degrees, whereas for buoyancy resonances, it is usually very small, especially near the planet, and that is one of the main characteristics of the buoyancy resonances. So we believe that buoyancy resonances explains these observed spirals in TW Hydra much better than the traditional Lindelblad resonance theory. And another hint is that this is now VLT observation in infrared. And if you look at this part here, this gap at 1.5 arc second, this is at about 90 AU. So we believe that there's some decrease in density in small dust grains there as well. So it is also consistent with the idea that there's a planet at around 90 AU. So here's my takeaway point. In addition to the spirals driven by Lindelblad resonance, planets can excite spirals through buoyancy resonances. And two main characteristics are they are very tightly wound and they induce large vertical perturbations of order of few tens to 100 meters per second, which we can observe with ALMA. And based on the morphology, we propose that there could be a planet, sub-Jovian mass planet at 90 AU in the disk.